In this problem, we're being asked to identify if, based on a sample of 137 randomly selected students, that the average expenditure per student at a certain school has changed. Okay, so let's take a look at the information given to us and see if we can develop a hypothesis test and come to a conclusion about what is being claimed. So looking through this, we see that the average expenditure per student for a certain school year was $10,337. Okay, so this is our benchmark. And with a population standard deviation of 1560. Now, we have this survey of 137 randomly selected students that resulted in a sample mean of 10,590. Now, 10,590 is definitely different than 10,337. But we know that when we take samples, our samples aren't going to always perfectly exactly match our population because there's variability from sample to sample. The question is our sample different enough to say, hey, something's changed? Right? So let's walk through the hypothesis testing process to determine that. So one of the very first things we do is we set up our hypotheses. Now, to set up our hypotheses, we want to set up our null hypothesis and our alternative hypothesis. Our null hypothesis is always a statement of equality. It's always that our population still equals that original benchmark, 10,337 in this case. Our alternative hypothesis is always a statement that says something has changed. Now, sometimes what's changed is that the mean has gotten bigger. Sometimes what's changed is that the mean has gotten smaller. In those cases, I would use a greater than or a less than symbol. But in this case, it just says, has the average expenditure changed? So instead, I'm just going to go ahead and use a not equal to. In other words, it's no longer equal to 10,337. Okay? Now, what are we actually claiming? The question here at the end says, do these results indicate the average expenditure has changed? So we are actually interested in proving whether or not something has changed, and that's my alternative hypothesis here. Okay? So that is our claim. Our claim is that the average expenditure per student at this university or at this school has changed, meaning it is no longer $10,337. Great, so we've got that set up. Now, because I am interested in the fact that it doesn't matter whether it's gone up or down, I'm just curious, has it changed? We call this a two-sided test. Now, if this statement had said, do these results indicate that the average expenditure has increased, or do these results indicate that the average expenditure has decreased, that would be a one-sided test because I'm only interested on whether it's increased or whether it has decreased. So that would be a one-sided test. And in the textbook, it goes through the differences between those two and the slight changes that you have to make. Now, here's a key statement down here. The very last piece, alpha equals 0.01. That is the value right there. I'm going to write that down right over here. Alpha, wrong tool, alpha equals 0.01. This is the value that dictates where our critical values are. Now, our critical values are these values that come from or that serve as a purpose to define whether or not the sample is different enough to reject the null hypothesis and accept the alternative that something has changed. Because remember what we said at the very beginning? We know from sample to sample, you're going to have a little bit of variability from the population. But if the variability is big enough, we can say, something's at work here different than just random variability. I always like to draw the normal curve and put dashed lines to represent my critical values. Okay? Now, critical values come from this value of alpha equals 0.01. Now, this goes back to the previous section when you were working on confidence intervals, right? When you're dealing with a two-sided test, your confidence intervals and your hypothesis test critical values, you find essentially the same way. We remember back to a confidence interval of alpha equals 0.01, that the z-score was 2.58. So guess what? That's going to be our critical values here, 2.58. If alpha was 0.05, we were at a 1.96. And there were some other very common values where you hopefully got used to seeing similar z-score values. So 2.58. This one should be a negative down here. So we know that this alpha 0.01 means we want to be 99% confident. Well, if we want to be 99% confident, that has to fit within 2.58 standard deviations each way from the center. Again, a lot of similarity there to the confidence intervals, okay? So now these critical values are important because they define our accept and reject regions. Everything in the middle here is our accept region. And everything out here, reject and reject. Okay? In other words, we're going to calculate our test statistic next. If our test statistic is greater than, if it's a bigger value than our critical values, that puts us far away from the center, which means we've got a big difference. I'm going to reject my null hypothesis and accept the claim that something has changed. However, if my test statistic is less than my critical values, if it's within that range, I'm going to just say that the difference between the population and the sample is just normal random variability. So let's go ahead and do that test statistic. Our test statistic here is the z-score. So z is going to equal, okay, let's see, we always do the sample first. So that's the 10,590. Okay, minus the population. So minus 10,337. And we divide that by our population standard deviation, 1560, divided by the square root of our sample size, I believe it was 137. Okay, so going ahead and working this out, get my calculator out here. We're going to do 10,590 minus 10,337. Get that answer. We're going to divide that by 1560 over the square root of 137. And I'm getting a value rounded to 2 decimal places of 1.90. So I'm getting a z-score of 1.90. This now is the value that I say, let's take this value and compare it to the critical values that I drew here on my normal curve. And there's a reason I drew it to the middle, because 1.9 is indeed between these two values. It's in the acceptance region. Okay. Now, remember, the accept and reject are always in context of your null hypothesis. It's telling us whether we accept or reject the null. This test statistic of z equals 1.9 is telling me that I have to still accept my null hypothesis, which means I cannot support the claim of my alternative hypothesis. I'm in the acceptance region right here. Okay, so remember, what we're doing is we're always looking, is the difference between our sample and our population big enough to say that there's actually a significant difference, or is it just normal random variability of sample to sample? In this case, we're saying that the difference between the 10,590 and the 10,337 is a small enough difference to say it's just normal random sample variability, which means we have to continue to accept the null hypothesis. Okay, so we are going to say accept the null hypothesis. And the claim that we can make, or the summary that we can make, is there is not enough evidence to support the claim that the average expenditure has changed. So there's the process of doing a two-sided hypothesis test.